December 9th, 2025. For 60 years, Japan's earthquake monitoring network has tracked thousands of tremors without ever triggering its most serious protocol. Until tonight, a magnitude 7.6 rupture off Honshu's coast just activated the nation's first ever Megaquake warning system, and the probability calculations are sending shockwaves through the scientific community. The tremor wasn't exceptional. What came after was. Stress analysis shows the quake redistributed pressure across multiple fault segments, spanning 600 kilometers of seafloor. GPS stations are recording millimeter-scale shifts in real time. Seismic sensors are picking up rhythmic pulses that mirror the exact pattern detected before the 2011 civilization-altering disaster. And buried in classified government models lies a prediction too dangerous for public release. If these connected fault systems rupture in sequence, the resulting tsunami could reach heights of 98 feet and kill nearly 200,000 people within hours. Are we witnessing the opening phase of the Pacific's next great catastrophe? Or has Japan's early warning system just saved millions of lives by detecting what no earthquake network has ever caught before? Japan sits at the intersection of four tectonic plates: the Pacific, Philippine Sea, Eurasian, and North American plates. This convergence zone has generated some of Earth's most devastating seismic events across recorded history. Over 1,000 years ago, the 869 Jogan earthquake triggered massive tsunamis that penetrated 4 kilometers inland, establishing the historical precedent for megathrust ruptures along the Japan Trench. In 1896, the Meiji Sanriku earthquake generated 38-meter waves that killed 22,000, proving Japan's fault systems could produce civilization-ending disasters with minimal warning. 1923 brought the Great Kanto Tremor, a magnitude 7.9 quake that devastated Tokyo and Yokohama, killing 105,000 and demonstrating how seismic disasters could collapse entire economic regions in minutes. But it was the 2011 Tohoku catastrophe that reshaped global perceptions of geological risk. The magnitude 9.1 Megaquake became the most powerful ever recorded in Japan, generating 40-meter tsunami waves that killed nearly 20,000 people and caused $360 billion in damages, the most expensive natural disaster in human history. Dr. Kenji Satake of the University of Tokyo explains, each major rupture teaches the same lesson. Japan's fault networks don't act independently. They respond to stress like instruments in a geological orchestra, and when they play together, the consequences reshape entire coastlines. Historical analysis reveals these disasters follow predictable patterns. Major ruptures occur every 500 to 1,000 years along specific fault segments. The 2011 disaster occurred exactly 1,142 years after the Jogan event, suggesting these systems operate on cyclical stress accumulation patterns that span millennia. Japan's seismic patterns reveal a terrifying consistency. Major ruptures do not strike randomly. They follow systematic sequences that seismologists can now trace with mathematical precision. Historical data shows that 73% of Japan's major earthquakes of magnitude 8.0 and above were preceded by significant foreshocks within 48 hours. The 2011 disaster followed this pattern exactly. A magnitude 7.3 tremor struck on March 9th, 2011, followed by a magnitude 9.1 catastrophe on March 11th, 2011. Advanced GPS and seismic monitoring reveal how energy transfers through Japan's interconnected fault systems. When one segment ruptures, it redistributes pressure across neighboring faults, like dominoes arranged in a geological chain reaction. Dr. Yoshiaki Takahashi of the Japan Agency for Marine Earth Science explains that we have identified what we call seismic corridors, pathways where stress propagates through the crust at measurable speeds. These corridors connect the Japan Trench, the Kuril Trench, and the Nankai Trough into a unified threat system. Modern instruments also detect rhythmic seismic pulses that appear across multiple fault segments simultaneously. These heartbeat patterns indicate pressure buildup reaching critical thresholds across interconnected networks. Government models identify three primary scenarios for systematic failure: sequential triggering, one major rupture triggers adjacent faults within hours; synchronized release, multiple segments rupture simultaneously due to shared stress; progressive collapse, stress migration causes delayed ruptures spanning weeks or months. The most dangerous pattern involves coupling between the Japan Trench and the Kuril Trench, where northern and southern fault systems can trigger each other across distances exceeding 1,000 kilometers. Since 2020, Japan's seismic networks have recorded increasing micro-pulse activity. These are subtle rhythmic tremors that historical data shows accelerate before major ruptures. The December 9th, 2025 earthquake occurred during the highest micropulse activity recorded since 2011. At 11:15 p.m. local time on December the 9th, convenience store owner Nobuo Yamada was closing his shop in Aomori when the ground began to twist beneath his feet. He later told NHK reporters, "I have never experienced such shaking." What Yamada did not know was that he had just witnessed the activation of Japan's most sophisticated earthquake monitoring system, detecting patterns that matched their worst-case scenarios. Within 3 hours of the magnitude 7.6 earthquake, Japan's meteorological agency activated a protocol they had hoped never to use, the nation's first systematic Megaquake advisory. This was not a prediction of when disaster would strike, but a mathematical assessment that probability thresholds had jumped to historically dangerous levels. Advanced monitoring stations recorded stress redistribution across 600 kilometers of seafloor fault networks. Global Positioning System satellites detected ground movement patterns identical to those observed before the 2011 catastrophe. Seismic sensors captured rhythmic pulse sequences that government models correlate with cascading rupture preparation. Dr. Hiroshi Nakamura of the National Research Institute for Earth Science described the readings as evidence that multiple fault segments were responding to the same pressure wave. He said the stress signatures mirror mathematical models that predict systematic fault failure and that this was not ordinary aftershock activity. Classified government simulations model the worst-case outcome if the Japan Trench and Kuril Trench systems rupture in sequence. The resulting tsunami could reach heights of 98 feet, travel at speeds exceeding 500 miles per hour, and strike coastal communities with less than 20 minutes of warning. Modelling equivalent to FEMA predicts up to 199,000 potential fatalities across the impact zone. Economic damages could exceed $200 billion, surpassing 2011's record as the most expensive natural disaster in history. On December 9th, the tremor triggered automatic safety protocols at multiple coastal nuclear facilities. Workers were evacuated from Fukushima monitoring stations as a precautionary measure. The same tsunami scenarios that threaten coastal populations could overwhelm nuclear cooling systems across northern Japan. Tsunami propagation models show how a Japan Trench rupture would trigger alert systems across the Pacific Rim within hours. Hawaii faces 7-hour wave arrival times. California's coastline could experience 12-foot surges. The economic disruption would ripple through global supply chains dependent on Pacific shipping routes. Government seismologists are privately comparing current stress patterns to readings taken 48 hours before the 2011 disaster. The mathematical correlation is exact enough that some researchers believe Japan's monitoring network has detected the kind of systematic threat that occurs once per millennium. As of December 22, 2025, Japan maintains its Megaquake advisory, while seismic stations continue recording stress migration patterns. Over 182 municipalities from Hokkaido to Chiba Prefecture remain under enhanced preparedness protocols. The question haunting the scientific community is not is not whether these fault systems will rupture together. It is whether Japan's early warning breakthrough has provided enough time for 199,000 potential casualties to recognize the signs and evacuate before the seafloor moves again. The December 9th earthquake revealed vulnerabilities that extend far beyond seismic damage. Japan's coastal infrastructure sits directly atop the world's most dangerous geological intersection, creating cascading failure scenarios that could destabilize entire regions. 17 nuclear reactors operate within the projected tsunami impact zone. The 2011 disaster proved these facilities cannot withstand megathrust tsunami scenarios. Current safety protocols call for immediate shutdown and evacuation if tsunami warnings exceed 10 meters, but the 98-foot worst-case scenario would overwhelm all existing countermeasures. Japan's ports handle 40% of global container shipping traffic. The port of Tokyo, Yokohama, and Sendai process over 200 million tons of cargo annually. A systematic tsunami strike would sever supply chains connecting Asia, North America, and Europe for months. Underwater fiber optic cables carrying 95% of international internet traffic pass directly through the fault zone. The 2011 tsunami severed multiple cable systems, disrupting global communications for weeks. A larger event could isolate entire continents from digital networks. Government models predict second-order effects extending across the Pacific. In Hawaii, 42,000 residents are in evacuation zones, and waves could arrive in 7 hours. In California, damage to port and coastal infrastructure is estimated at $15 billion. In Alaska, native communities with no evacuation infrastructure face 30-foot waves. Dr. Kenji Hirata of Tohoku University warns that we are not just modelling a Japanese disaster. We are looking at a systematic failure of Pacific Rim infrastructure that supports 3 billion people. The economic disruption alone could trigger a global recession. Japan's sophisticated monitoring network can detect systematic threats, but it cannot prevent them. The December 9th Megaquake advisory represents humanity's first real-time observation of a potential civilization-scale geological disaster in preparation. Current stress monitoring shows continued pressure accumulation across connected fault networks. Each day without a major release increases the potential energy available for catastrophic rupture. On March 11, 2011, at 2:46 in the afternoon, the magnitude 9.1 Tohoku earthquake began. It lasted 6 minutes and moved Japan's main island 8 feet eastward. The energy release was so massive that NASA calculated it shortened Earth's days by 1.8 microseconds and shifted the planet's axis by 6.5 inches. The tsunami that followed travelled at 500 miles per hour across the Pacific, reaching heights of 133 feet in some coastal areas. Entire towns like Minami Sanriku and Rikuzentakata were erased from the map in minutes. The waves travelled 6 miles inland, overwhelming seawalls designed to withstand once-in-a-millennium events. But the most terrifying aspect was the systematic failure cascade. The tsunami disabled cooling systems at Fukushima Daiichi, triggering the worst nuclear disaster since Chernobyl. 3 reactor cores melted completely. Radioactive contamination forced the evacuation of 154,000 residents within a 20-kilometer radius. The economic impact rippled global. Supply chains connecting Japan to automotive, electronics, and manufacturing industries worldwide collapsed overnight. Economic losses exceeded $360 billion, but indirect costs through disrupted international trade may have exceeded $1 trillion. Historical analysis reveals that 2011 followed the same foreshock sequence now observed in December 2025. The magnitude 7.3 precursor earthquake occurred exactly 48 hours before the main rupture, identical timing to current stress monitoring data. What makes 2025 potentially more dangerous is the expanded monitoring network. In 2011, scientists missed early warning signs that current instruments can detect. The systematic threat recognition capability means we are now observing geological processes that previous generations could only study after catastrophic failure. If the December 2025 patterns continue following the mathematical progression from 2011, Japan's fault systems may be approaching critical stress thresholds not seen since the last great cascading rupture over 1,000 years ago. Japan's fault networks do not exist in isolation. They form part of the Ring of Fire, a 40,000-kilometer chain of volcanoes and fault systems that encircles the Pacific Ocean. When major segments rupture, the stress redistribution can trigger seismic activity across hemispheres. The 2011 Tohoku earthquake triggered measurable seismic responses in California, Alaska, and even the Andes Mountains. Stress waves traveled through Earth's crust at speeds exceeding 8 kilometers per second, arriving at distant fault systems within hours. Recent research by the Stanford University Seismic Network shows how Japan's December 9, 2025 earthquake generated stress pulses detected at monitoring stations across the Pacific Rim. The Cascadia subduction zone off Oregon recorded synchronized tremor patterns within 6 hours of Japan's rupture. On July 29, 2025, a magnitude 8.8 earthquake struck off Russia's Kamchatka Peninsula. Within hours, seismic monitoring stations detected coordinated responses across multiple volcanic arcs from Alaska to Japan. The systematic nature of these responses suggests interconnected geological networks spanning thousands of kilometers. Dr. Elena Kozlovskaya of the Russian Academy of Sciences observed that we are documenting real-time evidence that Pacific fault systems communicate through stress wave propagation. What happens in Japan does not stay in Japan. Pacific Rim nations process 80% of global shipping traffic and generate 60% of worldwide gross domestic product. A systematic rupture cascade beginning in Japan could trigger economic disruption comparable to global pandemic scenarios. The December 2025 Megaquake advisory represents humanity's first opportunity to observe systematic geological threat development in real time. Previous civilizations experienced these events as sudden catastrophes. Current monitoring capabilities reveal them as mathematical progressions with predictable stress accumulation patterns. The question is no longer whether Japan's fault systems will rupture together. It is whether global infrastructure can withstand the cascade when they do. Japan's early warning system has detected something unprecedented: systematic stress patterns identical to those preceding civilization-altering disasters. Are we witnessing the countdown to the Pacific's next great catastrophe, or has scientific monitoring finally given humanity the tools to recognize geological threats before they strike? What would happen if these fault networks ruptured tonight? Would global infrastructure survive the cascade? Drop your thoughts below and subscribe to stay informed as this story develops. Don't wait until it's too late. Subscribe to Earth Attacks now and arm yourself with the knowledge that could save your life. Yes, our channel is dedicated to uncovering the hidden dangers beneath Earth's surface, providing the most up-to-date and accurate information about the geological threats that could strike at any moment. From mega earthquakes to civilization-ending tsunamis, Earth Attacks is your ultimate source for staying one step ahead of the planet's most devastating forces. In a world where early warning can mean the difference between life and death, subscribing to Earth Attacks is not just a choice, it is a necessity. Join our community of informed survivors today and never be caught off guard by Earth's next attack.